Good evening, friends. Since I was little bit busy at the morning, I was not able to send you the video. Uh, Let it be. We are dealing with the chemical equilibrium. Today, we will talk about the perfect gas equilibrium. Perfect gas equilibrium. Perfect gas equilibrium or perfect gas equilibrium. So, what is the perfect gas? Perfect gas is the ideal gas. Ideal gas is which one? The gas which obeys the ideal gas law, that is called as the ideal gas. Real gases are different and ideal gases are different. Since we are learning the chemical equilibrium, we will be dealing with only the equilibrium. Suppose A is the reactant gas, that is ideal gas. It is reactant molecule is going to convert into the product after some time. Again it is forming the B as the ideal gas. So this B ideal gas again reacting and it is again forming the A, that is again ideal gas. So both of A and B are the ideal gas. Now delta G for this reaction, delta G for this reaction will be, we know that G of B, that is gives free energy change for the product minus gives free energy change for the reactant B. So Ga is equal to what? Ga, that is gives free energy of the reactant, that is equal to G0 of A plus RT ln Pa, and G of B is equal to G0 of B plus RT ln Pb. Now, what are those terms? This is the standard state, gives free energy in their standard state. For the A gas, this is the gives free energy in the standard state of the B gas. R is the molar gas constant, T is the temperature, ln, that is log, Pa and Pb. What are these Pa and Pb? These Pa and Pb are the partial molar pressure, partial molar pressure of that gases, partial molar pressure of that gases. Now, suppose this is equation number 1 and this is equation number 2 and this is equation number 3. If you put this equation 1, 2 and 3 in equation number 1, that is instead of G and Gb, delta G, that is equation 1 becomes delta G is equal to G0 of A plus RT ln Pa, that is partial pressure Pa, minus G0 of B plus RT ln Pb. Now multiply this by minus sign, that is delta G is equal to G0 of A plus RT ln Pa minus G0 of B minus, since we are multiplying with the minus, that is minus RT ln Pb, RT ln Pb. Right. Now this Ga and Gb uh, uh, can be taken into the bracket since these are the similar term. Otherwise we can multiply this equation by minus sign. Suppose this equation number 4, apply this equation number 4, multiply equation 4 by minus sign. What will get? We will get delta G is equal to minus G0A minus, this side also minus, since it is delta G, change as it is, and delta G, so I have not written it there. Again the difference comes, whatever difference that may be the minus or positive, negative or positive. So we are multiplying this equation by minus delta Ga minus RT ln Pa. Now this big minus will become plus G0B plus RT ln Pb. So what next? Next, next is delta G is equal to minus Ga plus Gb, that comes out to be G0b minus G0a plus RTLN PB minus RTLN PA. Now this G0b and G0a are G that is equal to this delta G, that is equal to delta G. Therefore that comes out to be, that is one and the same, that is this equation delta G we can write instead of GB and GA, sorry, GB, here it is A. So that comes out to be delta G is equal to delta G0, we can write delta G0 is instead of delta G0 in the standard state, that comes out to be RT ln PB divided by PB divided by PA. Therefore that is, again this PB divided by PA is equal to delta G is equal to delta G0, delta G, and what is the difference between delta G and delta G0? Delta G0 is the gives free energy in the standard state, and this is the gives free energy, this is the gives free energy, and this is the gives free energy in the standard state. Therefore delta G0 plus RT ln PB RT ln PB divided by PA is equal to Q. This Q, where Q is equal to PA divided by, sorry, PB divided by PA. PB divided by PA. Remember that. This is called as the constant factor. Quotient factor. Quotient factor. Now this quotient factor, now this equation is, remember that this equation delta G is equal to delta G0 plus RT ln Q plus RT ln Q. How we have written here? PB divided by PA. Since this is minus term in terms, therefore plus RT ln, these two terms are same, therefore PB divided by PA. So we have written here PB divided by PA. Now this quotient factor is similar to that of the whatever equilibrium constant value. Quotient factor is similar to that of quotient factor what we have written last equation, that is delta G, is equal to delta G0 plus RT ln PB divided by PA. What are these PB and PA? These are the partial molar pressure, right, of that particular gas in that mixture. Which mixture? Where A and B gases were coexisting. So PA and PB, that is equal to Q, that is delta G is equal to delta G0 plus RT ln Q, where Q is called as the quotient factor. I have already stated that quotient factor. So this quotient factor is similar to that of Kc. What is this Kc? Kc is the equilibrium constant. In the last lecture we have derived. Kc is the equilibrium constant. If the concentration, if the reactants are expressed in the concentration, then that is Kc. If the reactants are expressed in the pressure, partial pressure, then that is Kp. So but the values of this Q and Kc, that is equilibrium constant value, and this quotient values are not the necessarily same, but the comparison between Q and Kc gives the greater idea of about the given reaction. Is what? If Q is less than Kc, then the reaction proceeds toward the forward direction. Reaction proceeds to the forward direction. Forward direction. How come reaction proceeds to the forward direction? A gas gives B gas, and B gas again reacts and it is forming A gas. If this Q, that is question factor, that is this factor, that is this factor, we have derived from this equation. If the Q is less than Kc, then the reaction proceeds toward the forward direction. If Q is greater than Kc, then the reaction proceeds toward the backward direction, reverse direction. Reverse direction. Reaction proceed toward the reverse direction. If Q is equal to Kc or Kp, in that case, the reaction is at the dynamic equilibrium. The reaction is at the dynamic equilibrium. The reaction neither proceed forward direction, the reaction does not proceed reverse direction. Similar case is for the gaseous reactant molecule. In the gaseous reactant molecule, instead of Kc, we are writing the Kp value. Right? Now, we will see the real example. For example, the ammonia gas molecule, formation of the ammonia gas molecule in the Haber's process. For the gaseous real gas molecules, this equation was for the ideal gas molecule. Next one is the real gas molecule. We know that N2, that is gas, reacts with H2, that is hydrogen, it is again gas. How many number of H2? 3 H2. The reaction is reversible one. How many number of moles of NH3 gases are formed? 2 number of moles of NH3 gases are formed. Now this N2 is gas, hydrogen is gas, and ammonia is gas. Therefore, I will write this Kc. Kc is equal to, we know that we have learned how to write the equilibrium constant value for the given equilibrium reaction, that is product divided by reactant, that is how we write. Concentration is written in the square bracket. NH3, it is not written gas, 2 square, since there are 2 number of molecules. Then concentration of N2 into concentration of H2 raised to how much? It is 3, since there are 3 number of moles or 3 gas molecule, hydrogen gas molecules are reacting. Now this concentration of NH3, nitrogen, hydrogen, this Kc is written. If this concentration of nitrogen, ammonia, hydrogen are given in the moles per liter. If these gases are given in the pressure, that is in the bar, that is in the atmosphere, partial pressure, then this Kc is written Kp is equal to what? Pressure we have to write. P of NH3 square divided by square what? 2 number of ammonia molecule. Next one is P of N2, that is partial pressure of N2, then next multiplied by partial pressure of H2 raised to how much? It is 3, since 3 number of moles of hydrogen molecule are reacting. In this case, the ammonia, hydrogen, nitrogen, these gas molecules are expressed in the partial pressure, Pascal, bar or atmosphere. These are the units of the measurement of the partial pressure. So this is the real example, that Kp we can determine or Kc we can determine. Now let's try to solve some of the reactions. Suppose we'll solve the problems. We'll go through the first. We'll go through the simple problem, then we'll go the difficult problem. Write the equilibrium constant for the following reaction. Write the equilibrium constant for following reactions. Equilibrium constant for the following reaction. Number one, KClO3 that is solid reacts. It is again we are learning the equilibrium reaction. It gives KCl as a solid plus 3 by 2 O2 as a gas. 3 by 2 O2 as a gas. Now calculate the number of atoms to the right hand side as well as number of atoms to the left hand side. Next reaction is CaC2 as a solid plus 5O2 as a gas. 5O2 as a gas. Then this 5O2 as a gas, that is forming the product 2 CaCO3 solid, CaCO3 solid, calcium carbonate solid plus 2CO2 gas, 2CO2 as a gas. Number 3 H2 hydrogen as a gas plus I2 as a gas, iodine as a gas, that is again it is the reversible reaction. Then they are forming 2HI as a gas. Now we will solve one by one. We will solve Kc or Kp. If it is pressure, if it is gas, we can write Kp, equilibrium constant value, Kp or Kc. If the gases are involved, we can write Kp. If the liquids are involved, we can write Kc. Now this Kp is equal to, for number 1 reaction, we know that. What do we know that? Product divided by reactant, that we have learned. This is the solid. Since it is the solid, we have to write in the concentration term KCl, solid. There is no number of molecule, only one number of molecule. No, it's only one number of molecule. So no need to give the power of that into this. How much? This is the gas. So we cannot write in the concentration. Therefore, pressure of O2, PO2, pressure of O2 raised to the power how much? 3 by 2. Raised to the power 3 by 2 divided by, this is the solid. Therefore, we have to write again into the concentration term KClO3 concentration. This is the equilibrium constant, right, for the first reaction. Next, for the second reaction, we will write here. For the second reaction, Kp is equal to what? Kp is equal to, for the second reaction, as I told you that if it is the gas, we have to write the pressure. If it is the solid or liquid, we have to write the concentration. 2 calcium carbonates are formed. So calcium carbonate is the solid. Therefore, CaCO3, how many? 2. Therefore, raised to the power 2. Now, this is the gas. So PCO2, how many? Raised to the power 2 divided by what? CaC2, that is solid. Therefore, CaC2, only one number of molecule. Therefore, no need to give the power. Now, this is again the gas. Therefore, we can write PO2 raised to how much? Raised to 5. Right? This is the equilibrium constant value. Number third equation we can also write. That is very simple. Kp, if it is pressure involved, we are writing the Kp. So product, that is HI, sorry, it is the gas. Therefore, how we can write? PHI, concentration of PHI, pressure 2. Therefore, square divided by H2, only one gas, H2, but it is the gas. Therefore, we are writing PH2 complete. Then next one is again, this is the gas. So PI2. So these are the equilibrium constant value. We will solve the more problem in the next lecture. Thank you. Bye bye.